Hi everyone. In the previous video, I think it was 01H20, we finished up talking about epoxides, how to make epoxides and how to ring open them. For this video, I want to go over a couple of examples, some practice problems, and yeah, so this is 01I20, and the first one I want to do is how do we make cis and trans diols using what we've learned in the epoxide unit. So the problem could be something like from this alkene, okay, make, and I'm going to have one set that's cis and one set that's trans. And the one that's cis, I'll make it look like this. I want us to take cyclohexene and make cis diol, cyclohexane diol. Now, this is specifically called a vicinal diol. Vicinal meaning neighboring. Not on the same carbon, and vicinal diol. Now, I could have drawn these dash and dash, but actually, since this is symmetrical and it has a plane of symmetry, the dash dash is actually identical to this. All you have to do is flip it. So that's the cis, but I also want us to make the trans. Now, the trans actually can be two enantiomers. It can be one of two enantiomers. It could be this enantiomer, or it could be the opposite. The OH dash on top, the OH wedge on the bottom. These are actually not identical. Not identical. They are, here's what the term for this is. These are enantiomers. They are mirror images of each other that are not superposable. All you have to do is flip this one to the left. Okay, just turn this one over, and then the OHs will mirror each other with the correct wedge dash. The other term that you might remember is that if you make a mixture of enantiomers, that's called a racemic mixture. Okay. So one of our syntheses, we are going to make a racemic mixture of trans. This is trans. Let me show you how to do these syntheses. And actually, the first one is only one reaction, so it's not really a synthesis. It's more of a fill in the reagent. This is not using an epoxide strategy. This is recalling our reactions from the alkene unit, and it's osmium tetroxide with NaHSO3, sodium bisulfite. Okay. Some textbooks and some web pages put 1 and 2. Some textbooks, instead of this reagent, they have water and H2O2. This is the combination that I like. If a student gives me just osmium tetroxide, then I would probably count it as correct also. Well, we have this. Osmium tetroxide makes a diol that makes a cis diol, and I'm going to draw the OH wedge off of the two carbons that are part of the double bond. Now, if you're super concerned about stereochemistry, you may, I've seen students do this, draw the dash dash. Right? It's just as likely that the oxygens will be from the bottom, from underneath the table. But this will be considered incorrect because this is implying that you have two distinct products, whereas these two are in fact identical. So either make it clear to your grader that you know that these are identical, or maybe safer, just only draw one of them. But what about the transversion. What about the transversion? Well, we're going to use an epoxide strategy, and I'm going to use MCPBA. Sometimes that M is lowercase, but it really doesn't matter. This is a peroxy acid. Recall from your notes that if you use a peroxy acid, it doesn't have to be MCPBA. It could be methyl peroxy acid. You'll make an epoxide. Now the epoxide, let's see. Try to figure out if the epoxide doesn't matter whether they're both wedges or both dashes. Well, the cyclohexene has a plane of symmetry, and this has a plane of symmetry. This is achiral. This is achiral, and if you had drawn dash dash, it's the same thing like up here, that it would be identical. Okay. So I'm just going to keep this one, right? If you draw the dash dash, that's fine, but only draw one or the other. And now, how do we get this to be a diol? There are two main ways. One is where you have no acid. If you look at the last video, the previous video, I never said that the reaction is basic. What I do say is that it's run under the absence of acid or no acid. Okay, I just want to make that clear. It doesn't have to be basic. It just has to be not acidic. Not acidic enough to protonate that oxygen. Okay. Now, I chose an epoxide that has a plane of symmetry, so it doesn't matter whether you attack the top carbon or the bottom carbon. So I'm not worried about regiochemistry. I'm worried about stereochemistry, right? I want the trans. The OH minus, there's no strong acid in this case, will attack the less substituted carbon, but in this case it doesn't matter. What always matters is that the nucleophile attacks from the back side. Not always dash. What I mean is that it attacks from the opposite side of where the oxygen is. So I'm going to pretend that it attacks the top carbon. The OH attacks, opens up the ring, and the other O is wedge that gets protonated by the water. So that would assume that the OH would attack from the top. But if the OH attacks at the bottom, again, from the backside, you'll get the enantiomer. The OH adds there, and then the wedge O is up here, which initially was a negative alkoxide, and then you protonate with water. These two are actually different. Okay, they're different, and hence they're different in their enantiomers. Hence, this is a racemic mixture. So where are our products? Osmium tetroxide gives me this, okay. And then showing all the organic products, the epoxide method gives me that. Those of you who are studying epoxide chemistry, I did not talk about regiochemistry. I did not talk about attacking the more substituted or less substituted. I'm trying to figure out how much time I have. Okay. So why don't I, for the next couple examples, focus on that, the regiochemistry. Where should the nucleophile attack? But also, what is the nucleophile, right? What is the nucleophile? Because here we have to know that it's actually OH minus that's the nucleophile. Now, before I actually do those examples, I have one more thing to say. You might recall that, well, sure, we added OH under non-acidic conditions, but can we do this under acidic conditions? Yeah. Just use water and add acid, like sulfuric acid or HCl. Okay. I'm not going to go through the mechanism. I think when we look at the other problems, you could apply those mechanisms to this one here. But I could verbalize it, or we could verbalize it together. Now we're under acid. So we're going to protonate the oxygen first, and then the water is going to attack the carbon. And it doesn't matter which carbon in this case. If it was not symmetrical, then the water would attack the more substituted carbon. So there are two ways to get this mixture, either in the absence of acid or in the presence of acid. Now, I don't normally do this, but in the previous video, I made a practice sheet for my class, and really the only problem on this practice sheet is the two problems that I gave at the end of this video, 01H20. Let me zoom out so we can see those two problems. And technically there are four. Okay, one, two different ways, and take this epoxide and react it two different ways. You see here, now it makes a difference because I could attack either the carbon on the left or the carbon on the right, and I'll definitely get different products. I could attack here the carbon on the left or the carbon on the right, and I would get two different products. Not only because the epoxide is not symmetrical, but also I'm not adding ultimately an OH. So for these nucleophiles, I'm not adding OH, and I'm not going to get two OH groups. I'm going to get an OH, the O from the original epoxide, and then another group, the nucleophile. If you don't have this sheet with you, you probably do if you took notes from video 01H20, but if you don't, go ahead and copy this, because I'm going to make the products on this sheet, and then if I have time, we'll look at the mechanism. But I actually want to go or show you my thought process to try to get these answered as quickly as possible. Okay, so we're going to pretend we're under test conditions. I am going to put a lot of notes. You obviously, when you take the test, you don't do that. Although, some of these notes you should do. For instance, let's start with the first one. If you're not very comfortable visualizing the nucleophile, then I would redraw it. See, my nucleophile is methoxide, because again, when you have a counterion metal, right, you're going to think that's ionic, okay, and ionic compounds, we're going to assume that dissociate. Your nucleophile is OCH3-. There's no acid here. Water can be an acid, but for epoxidations or epoxide chemistry, it's not strong enough to get a lot of oxygen protonated significantly. Not in significant amounts, at least, unlike with sulfuric acid. Okay. So what was the trick? No acid, attack the less substituted. The less substituted is this one because we have a methyl and an H, and here we have an ethyl and a methyl. We have two groups off of this dot. We only have one group off of this dot. Let me show you how I would draw this, though. Because most of our examples, even the one that we looked at today, the epoxide, the wedges and dashes are on the oxygen, or to the oxygen. Here I have lines to the oxygen. But I still have stereochemistry because we got to pretend that this oxygen is above these atoms here. Okay? So if I'm attacking right here, okay, the nucleophile, and I open up this ring, you see how the OH would be up here now, and the nucleophile would be down here. That's how I would start the drawing. On the left side, everything stays the same. On the right side, it's almost like, well, not almost, it's SN2 and it's inversion. A puff of wind comes from the bottom and pushes these two groups up. So you still maintain the wedge methyl and the dash hydrogen, but now that last group, okay, is down here instead of that O being up here. Now, those are two different O's, okay, but I'm saying that that's the fourth group of this carbon, right? Everything else stays the same, wedges and dashes, but now we attack from the bottom. That is the only product that I would expect. There's only one stereoisomer for this reaction. In purple, let me show you my thought process here. This is acid. You are going to protonate this first. Okay? So I know this is a little bit crowded because now I'm discussing a different mechanism for this reaction here on the same molecule. The nucleophile now is coming from the bottom still, from this side. What is the nucleophile? The nucleophile is this whole methanol. Okay, but let me draw it out first. O. I don't want to draw this. I'll draw it backwards. CH3, and now the OH is up here. Because I attacked the left side. Imagine if that H was still there. In the mechanism, the H would be there, but then also at the end of the mechanism, the last step, I would remove that hydrogen to make this oxygen neutral. If we kept this hydrogen here, that oxygen would be positive, right? And if we're using a neutral nucleophile, you know, for most cases, with a neutral nucleophile, you're going to remove that hydrogen eventually. Fill in your wedges and dashes. This would be a good time. We've seen one example. Why don't I ask you to pause the video, draw your wedges and dashes, and then unpause it and make your corrections when you see my answer. Okay. The right side stays the same this time. Exactly the same. Okay. Wedge dash. The left side, the wedge dash stays the same, but we're going to push them up. So the ethyl is still wedge, and the methyl is still dash. That's the correct answer for that. Yeah. We'll have time. Yeah, we'll have time to do the mechanisms, especially probably this one is the one that has the most steps. Let's take a look at this. Okay. So I'm going to go even faster, take less notes, because again, I want to see what the timing is when I do this on an exam. I want to do this under exam conditions. Why don't you pause the video and fill in the products? Don't draw the mechanisms. Fill in the products. You may want to take notes, or you may not. It's up to you. And I will meet you back after you unpause the video. Okay. So my video says we're at minute 18. Let me show you how fast that I would expect my students to complete these problems. Just drawing the product. So that was about a minute. If you have any different answer, go ahead and mark it wrong and put the correct answer in a different colored pen. Just beware that I could have obviously drawn the bromine going down. Right? It doesn't matter that carbon is not chiral, and I don't have wedges and dashes, and it really doesn't matter whether I drew the OH down or up, or however, just leave out the wedges and dashes. Yep, okay. What is important is that that bromine is wedge because it came from the opposite side of this oxygen when the ring opened. And this OH is actually dash because it kept the dash, because for the second reaction I attacked this carbon on the right. Alright. Let me show you the mechanism, and we'll do the easier one first. Let's do this one here. This is reaction D. Yeah, I'll do it on this paper. So D, no acid, and we have this molecule. I normally don't use wedges and dashes on a mechanism, but in this case, I'll make an exception just to show that the dash is going to stay dash. Why? Because without any acid, without this oxygen being protonated, your nucleophile, which you would have to know is Br minus, your nucleophile will attack the less substituted carbon. And then this will pop open. See, this carbon doesn't change. That carbon should remain dashed to the oxygen. It's minus, don't forget that. And the Br, you could draw it anyway. I'll draw it down. Doesn't matter. To protonate that, I had to be careful. I got to provide a proton source. So even though this is not acting like an acid to protonate this oxygen here, it will protonate this oxygen because this oxygen is more basic. It wants to be neutral. That is mechanism for reaction D. Let me show you mechanism for reaction B. Right, this one I said might be the one that's longer. This is reaction A, this is reaction B. If you want to go ahead and take a stab at it, that'd be great. You have your notes, you have your textbook, you have the problem, okay, right there, and you have the answer. You have the final product. If you want to go ahead and pause the video and do the mechanism on your own and double check, that would be great. That's a good sign. Okay, how would I do this? I allow my students to use H3O plus because there's always some water when you have sulfuric acid. Sulfuric acid is not sold neat. It's not sold pure, 100% pure. And I'll follow that. If you want to use H2SO4 as your acid, that's just as good in my book. But in real life, most likely it's hydronium that's doing the protonation. This is different than what we've seen. We didn't protonate first, the oxygen. That's new. We did not see that in the last mechanism. This is a little bit tedious, all the other groups, but there to illustrate regiochemistry and stereochemistry. Under acidic conditions, when you're protonating the oxygen, the carbon that's actually more attracted to the nucleophile is the more substituted carbon, because there's a bigger partial positive charge there. I wouldn't put this on a mechanism, but as notes, big partial positive, little partial positive. This oxygen is pulling electrons towards it to make this more neutral. But again, you don't have to put that on a mechanism. What's super important on the mechanism is you identify the correct nucleophile. And it's not just OCH3 minus. That's not the nucleophile. The nucleophile is methanol. You can't have CH3O minus when you're under acidic conditions anyway, right? It would just be protonated completely. So that has to be our nucleophile. It's neutral, and we're going to attack this carbon right here. What bond are we going to break? We're going to break this bond because we got to get this carbon back to only 4 bonds. How would we draw this? Well, your O H, whoops, is down there, and it's positive. Your OH is up here. That this group right here, that OH, now is on this carbon only. And we can see this right. Not H. Oh. Wipe this one out. When I study for exam, I'm pretty anal retentive. My notes need to be pretty clear when I study off of them. And my other side is like this. Okay. And then we gotta get rid of this hydrogen. What could we use? We could use water. Okay. We could use another methanol. Heck, we could even use another epoxide and protonate using this. But I think it's just easier to use water. We created water in the first step anyway. That actually. Now you may wonder, why is methanol attacking that water? Well, under these conditions, you're assuming that you have mostly methanol. But let's take care of this last deprotonation. And make sure we copy the product correctly. We did create acid, hydronium again. We should start the process over. Double check your answer. So we have this from the mechanism, and our answer is that. It is identical. With this video, 01I20, and the previous video, which was 01H20, I think we've seen maybe up to 6 different nucleophiles. If you count the differences between with acid and without acid, maybe 12 different nucleophiles. Just from this sheet here, right, we have OCH3 minus, we have CH3OH, methanol. This is not ionic. Okay, so if you're still confused about why didn't I make this CH3O minus, that's not ionic, this is ionic. For this one here, we have the nucleophile, once we strip off the H, is Br minus. And here, sodium and Br dissociate with the salt, and we have Na plus and Br minus. And so that's the nucleophile for reaction B. Look over your notes, take a look at the practice problems in your textbook, and get used to all of these different nucleophiles, whether they be anionic or neutral. And then we started out with a synthesis, diols, and don't forget the strategy here. A very popular question to ask: how to make a diol, a specific diol, either a cis or trans. And those are our methods down here. Okay, that might wrap it up for Unit 1. It's a big unit. Unit 2 is going to be pretty big also, aldehydes and ketones. So I'll see you all there.